Hello? Okay, hey everyone. We're gonna get started. So this is a deep learning workshop, and our demo of deep learning is gonna be about image classification. I'm Terry, and this is Charles, and we're gonna be the content committee members that are doing this workshop. So let's just get started. Basically, what we're doing in this hour is first we're gonna give an introduction to machine learning and deep learning, just for those of you that don't really have a lot of experience. It's completely okay. We have some slides that are that can go pretty in depth, but we're mostly just going to gloss over them so that we can get to the demo and try to get you guys as much information for the demo as possible. Okay, so let's start off some machine learning basics. So what is machine learning? It's the study of computer algorithms that can improve automatically through through experience or by use of data. And what we mean by automatically is that we're not explicitly programming the computer in order to learn, right? We're giving it some general algorithm in order for it to teach itself. And so we're talking about machine learning. We generally have two steps. We're either talking about training our model or doing some evaluation. So training would basically be taking our input data and then getting our improving our model's performance by letting the algorithm find patterns in that data. And the last part after training would be evaluation. So this is when the model is basically used, for example, in the real world in order to predict results from new data that's everywhere. And so if you're not really too familiar with machine learning, I came up with a kind of an acronym in that or not an acronym, but an example where basically if we have some machine, right, and we're trying to learn, the computer itself is like the brain. And the experience is our data. So we're feeding our data in as experience, and then finally we're learning to basically improve our model, and the learning algorithm or the learning method would basically be the computer algorithm that we design. Okay, so there's in general there's you can classify machine learning into a couple of different types. So the first two are really easy to compare and contrast: supervised and unsupervised. And the difference is the type of data that we have. So in supervised machine learning, the data is usually labeled. This means that, for example, if we're trying to do image classification or something, we're saying, this is an image of a cat, or this is an image of a dog. And we're literally telling the model what the right answer is. On the other hand, we have unsupervised learning. And so this is learning where the examples themselves, we're not actually providing an answer. And so what that means is that we're letting the algorithm find patterns and find answers and find hidden structures in the data itself. And then lastly is reinforcement learning. And so this type is a little bit different in that it's about teaching the model, or sometimes called an agent, to learn from its behaviors. And that it's gonna, the environment will punish the machine learning models, punish the bad behaviors and then reward the good behaviors. And deep learning, which is a subset of machine learning, is basically used in all three types. So there's deep supervised learning, unsupervised learning, and deep reinforcement learning. And so a super simple example of machine learning is actually linear regression, which comes from statistics. And a lot of machine learning actually comes from statistics. And so I was originally going to go super in depth into this, but since not everyone has mathematical background, and we simply in the interest of time, we're just going to go over this really quickly. So in linear regression, you're trying to define some linear relationship between two variables, right? The dependent and the independent. So for example, the classic example of linear regression is always trying to predict the price of a house, right? So for example, if we're using square footage to detect the price of a house, then you can see that we actually have two parameters that we need to learn for, right? And because whenever you're describing some kind of line, you have an intercept and you have a slope. And so our machine learning model, it's going to start off with random values for these zeros. And as you can see in the animation, you can't really see the line in the beginning because probably both of them were set to 0. So let's set them to some random value, right? And then as our machine learning model trains, we're adjusting these parameters in order to better fit the data. And you can see the line gradually gets closer to what we would see as the line of best fit in statistics. And so one question is how exactly do we know which direction to push our line in order to get the best result? And the answer to that is you need some kind of that concept of error or loss. And so one example of that is like mean squared error, where you find the square difference between the true value and your predicted value, and then you square that and you sum them all up, and that's basically your loss function. And then you use an algorithm called gradient descent in order to minimize that loss function. But we're not really going to go into detail, so if you're really interested in that, you can ask us after the presentation, and we'll be really happy to answer more questions about that. Okay, so next, like you might be wondering, like what exactly we're doing during training. Well, first you need to know that not all of our input data in machine learning actually goes towards training. So a common like split, for example, is to split up the data into training sets, validation sets, and testing sets. So training sets, as you can imagine, is literally used to train the model. Every iteration, we're passing the training set to the model in order for it to get better. But the point of machine learning is that we have this data, and we don't necessarily want our model to be like representative of the data exactly. We want our model to do well in the real world where there's new types of data. And so one common problem with machine learning is that our model becomes really adjusted to the specific values that we're feeding it. And that's called overfitting. And so to avoid overfitting, what we have is something called a validation set. And the goal of the validation set is to keep the learning in check so that the models are not overfitting, and we can basically abstract our answers to the real world. And then the testing set is just a set that we're using to finally determine the accuracy and evaluate the final performance of our models. Okay, yeah, so machine learning, it's widely prevalent across the world. And there's many examples that you can think of where you can possibly use machine learning. Basically, any case where you have a lot of data and you can use these data-driven algorithms in order to improve your model, you can use machine learning. And so, like for example, in image classification, which we're going to do later today, we're basically teaching a model through labeled images. We're going to feed the model images of digits, and then it's going to get better at recognizing those digits 0 through 9. And another one that I wanted to point out was actually search engines. So can anyone think of a reason why search engines use machine learning? Yeah, exactly, for patron. And use an important word, which is ranking. So basically, in search engines, we use a specific type of machine learning model called ranking models. And the point of those models is basically to rank the possible pages that we have to search, that the search engine provides, in order to basically provide the best user experience for the user who's doing a search. Okay, so now that we have some background, we're going to go into deep learning, which is like the most important topic for today. So the point of deep learning is that it's a type of machine learning that imitates the way humans gain certain types of knowledge using artificial neural networks. And we can actually relate these artificial neural networks a lot to basically the neurons in our brain. So there are like really two key ideas that we can take away from biology and then extrapolate them towards deep learning. This is what researchers have been doing for a really long time. And so the first is, if you take in biology, you remember that the neuron is the building block of the brain. And the point of the neuron is that it will receive signals from other neurons, and then those signals will accumulate until the neuron spits out some final answer to neurons that are coming after it. So that's the first most important step. But you may also remember from biology that not every neuron fires at every moment. And the reason for that is if a neuron does not receive enough input, then it will just not fire. And so that's the second basic idea that we basically have to be able to demonstrate. And so just as the neuron is the building block of the brain, we have something called a perceptron, which is the diagram to the left. The perceptron is the building block to artificial neural networks that we see today. And so what the perceptron does is it takes inputs from all the previous perceptrons in the previous layer, and it sums them using a weighted sum. So it takes, for example, in this case, we have y, we have z, and we have x, and each of those variables corresponds to a node in the previous layer. And then we're taking the sum of those inputs based on some weighted average W0, W1, and W2. And these are the values or the parameters that we're basically trying to learn in our machine, like deep learning model. And so that clears, step one, which was receiving inputs from other neurons. And step two is, we want to provide some way to represent that like activation energy, or basically to represent that if the previous neurons do not send enough signal, then I don't want this neuron to fire. And so the way we represent that is through an activation function. An activation function simply takes the inputs that the perceptron currently has from from the outputs of previous neurons, and then pass it through one of these possible functions. So, and these are not like this is not an exhaustive list. So we have like sigmoid, tanh, ReLU, and basically the idea of this is to add some non-linearity component so that our neural network is able to model very complex relationships. And so when we build up all of these, perceptrons into layers and layers, we can finally achieve our artificial neural network structure. Okay, so one big distinction between deep learning and machine learning is that a key step of machine learning is taken out, and that step is called feature extraction. If you remember and go back to our house prices example, if I were to try to like use some machine learning model to predict the price of a house, as a statistician or as an engineer, I have a lot of options for what kind of data I could choose, right? I could say, square footage was the example that I already used. Like I say, the number of bathrooms. If I have more bathrooms, then the price of that house may be greater. Or I can say like, oh, the direction that the main door faces, east, west, south, north, or whatever. Some people care about that, right? So maybe we can use that as a feature as well to make our model better. The whole point of deep learning is that the feature extraction step is completely skipped. So the reason for that is you can see how like in our deep neural networks, we have nodes, like hundreds of nodes. And it's possible that we may even have thousands of nodes. And the point of that is since we have so many nodes, we can completely skip the feature extraction part and let the neural network decide for itself what exactly is important and what is not important. And this may seem like really ambiguous and very vague, but that's actually what's going on here. So this neural network, the idea of the neural network is basically that you can put in all the input data you want, and the network itself will figure out what it thinks is important, what are the relationships between the variables, that can improve the final performance. And so one big advantage of deep learning is its size. So because neural networks are so big, the performance of these models compared to like traditional learning, machine learning methods scales much better with more data. As you can see with most learning methods that, we eventually reach some like kind of plateau in performance where like, no matter how much data you feed it, your model pretty much always does the same. But the opposite is actually true for deep learning. In deep learning, the more data we feed it generally, the better our performance is. And so a big reason for the rise of deep learning in recent years is because of big data, right? With so much data, we have a lot of data to feed these neural networks. Another reason for the rise of deep learning recently is basically since we have such large neural networks, we need to do large matrix calculations. And so basically since, if you've like heard of like the recent like graphics cards and stuff, those things have been going on since like in the research industry for like quite a long time. And basically those like access to better hardware has like allowed for a much like easier way to compute the calculations that are required for these deep learning models. And so next we're going to specifically talk about like some of the basics of these models, and Charlie's going to get more into that.
Okay, hi. So today we will be talking about the supervised learning model because it's very easy to use and it's very common and it's very friendly to beginners. So on this graph, you can see the whole model can be split into two parts, the bottom part and the upper part. So the bottom part is basically the forward path, and the upper part is basically the backward path. So we will be talking about the forward path first. So as you can see here, the forward path has been divided into three parts: the input, which is the data we have, the model result, and the output. So we can take that model as an example. So the input, we have an image of a bird, and we will divide that into pixels, which is just numbers, and we use the numbers as our input layer. And the input layers will traverse through the model, the hidden layers, and finally reach the output layer. So the size of the output layer is determined by the number of classes in the original data set. So let's say the original data set contains three kinds of classes: the dog, the bird, and the cat. So our final output layer will have three nodes, each representing one specific class. And after the data travels through the hidden layer, it will reach the output layer, and only one node will have the value 1, and the rest will have the value 0, which is, so the node with the value 1 is what our model predicts to be the output of the input class. Oh, sorry. And so for the hidden layers, there are a lot of type of layers we can use. So on this graph is the most common type of layer, which is linear layer, because the data travels in the linear sequence from left to right. And you can also have more complicated layers like residual network, which is basically the first layer is connected not to the second layer, but also to a third layer. So the model is nested and it's very complicated, but also can solve a lot more problems. And there are also two kinds of special layers I want to talk about. The first one is called redo layer. So a redo layer is basically a function that takes the input and its output. So if the input x is smaller than 0, the output will be 0. If the input x is greater than or equal to 0, the output will just be x. So we can see here in the graph is very simple. It's very simple to see. Before x equals 0, it's just y equals 0. And after x, after that point, it's just x equals y. And if we take a real life example, so if we have feature map with all the numbers, some positive, some negative, and we apply the redo layer, we can see all the negative numbers are not 0. So the reason why we have the redo layer is because without the redo layer, the whole model is just a huge matrix. All we are doing is linear transformation of the input layer, which is kind of boring, and not a lot of results can be achieved from that kind of model. So by adding the redo layer, it's called activation function, has some possibilities of things we can do. And the second layer we want to talk about is called dropout layer. So the idea is we apply the dropout layer after one of our layers, and it will randomly drop out some of the nodes, so that those nodes will not be involved in the calculation of the nodes in the next level. So here we have 6 nodes on that layer. So we apply the dropout layer. 3 of the 6 nodes are being dropped. So only the rest 3 nodes are actually being used to calculate the final layer. So without the dropout layer, there will be problems of overfitting, as we have talked about before. So now that we have completed our forward pass, we want to talk about the backward pass. So the backward pass is actually called backpropagation. So now we have our prediction y, which is output. We combine that with the true labels, and we send those two into a loss function to calculate the loss, which is basically how accurate is our prediction to the real value. And we will differentiate the whole network with regard to the loss, and for each weight, so each edge has its weight. So each weight, we have the gradient, which tells us how to update the weight in the next iteration. And we use the optimizer to do updates. And that basically completes the whole round of training, and we'll just keep doing that over and over again. So now I'm going to do a real short demo of training and pre-processing of our first linear classification model. So before we do the demo, we have to introduce the dataset we're using. So it's called MNIST. So MNIST is an acronym that stands for the Modified National Institute of Standards and Technology dataset. It's a dataset of 60,000 small square grayscale image of handwritten digits between 0 and 9. So the reason we choose that dataset is because it's very simple and it's very good for the demonstrating purpose of doing a linear classification model. So I will give you guys 20 seconds to go to that link.
Say that doesn't help. VHDL won't be not.
Is anyone still typing? Okay, good. So if you go to okay, if we go to the link, you can see there are 2 things here. One is a folder, one is a file. So I think you have to log in if you haven't, in order to see actually use the file. So I'll give you guys 3 seconds to log in if you haven't. So everyone is logged in? Okay. So if you right click the notebook and open with Google Collaboration. That's what you will be seeing, and you do copy to drive, which is copies the notebook to your own Google Drive. So you should be seeing this screen. And the first thing you have to do is you have to connect to a runtime in order to actually run the code. So you do connect. So you are connected to a runtime. Okay. And also you have to go to a runtime and change the runtime type. Make sure you are using GPU because the computational power GPU always will accelerate your training process a lot. So make sure you are doing GPU. Everyone good? Okay. So let's start our very short demo. So the notebook we're using is called Google Cloud. It's an online platform that allows you to run Python code in cells. So you can see the start button, you can just, that's how you run the cell. So first, you run the first cell to install the PyTorch, which is a library that's designed for the purpose of deep learning. It offers all the tools for you to make the process easier. So after you have run that, you run the second cell, which is basically a bunch of libraries that helps you to run the code. You have to wait for it to run. It might take a while. Okay, I'll wait for a few more seconds. Is anyone cell still running? Please raise your hand. Okay. Yeah, make sure you are connected to GPU. Otherwise, it will be super slow. I have it. Okay, so now let's start coding. So the first step is to build our model. So for our model, it will be, since we're doing a very short demo, so our model will just include 3 linear layers, 2 read layer, and 2 dropout layers. So here we have to first define our layers. So we do self dot retire linear 1. That's our first main layer. And we do nn dot linear. Now it has 2 parameters. The first parameter is the input size, and the second parameter is the output size. So we have to know our input size, the input size of our data. So I will just tell you guys here is 1 times 28 times 28. And for the output size, you can just put any number you want. But traditionally, we will just do a very large number, and we will decrease the number as we travel through layers. So let's just pick 3136. So that's our first layer, and the second layer will do the same thing, linear 2 and dot linear. But you have to remember the input of the second layer must equal to the output size of the first layer. So the input would be say 136, and the output we will just reduce the number. You can just use any number you want, but I will use 392 here. And we do the same thing for the third layer, and we do linear 3 equals n dot linear. So the input size will be 392, and the output size must equal to the number of class in your data set. Since we are doing digits from 0 to 9, the output size is 10. And now that we have all the linear layers defined, we will define our redo layer and the dropout layer. So redo is equal to n dot redo. And the dropout, we do the same thing. Yeah, capital letter dropout. I give you guys a few seconds to copy that down. Okay, so now we have defined our layers. We have to construct our model.
What was the question?
So we have to construct our model. So first thing first, we have to make sure the input is in the form of vector. So we will do a X view and so next the first parameter is -1 and the second one is 28 times 28, which is the size as we want. Okay, and now we start to construct our model. So we do X equals self dot linear. Yeah, whatever, I will just go without my mic. Can you guys hear me? Okay, so we will do self dot linear 1, and we passing X as our parameter. So now we have the input has traveled through the first linear layer, and we do X self dot, dot redo. Same thing, pass X as a parameter, and we do X equals self dot dropout, and same thing, pass X as input. So that basically finish one round of layers. So we just copy the whole block and paste it here and change the 1 to 2. Make sure you don't forget that. And lastly, we send X to the final linear layer. And we have our output. So we'll be returning X. So make sure you have the exact code. Otherwise, when you're doing the training, there will be a problem. Everyone got that? So don't forget to run your block. Okay, run cell. Okay, now that we have our model, we need to also check on GPU. So just run this cell. And you should be seeing that message. That means you have GPU enabled for your training. It might take a while.
You can just say your question.
I'm getting a lot of errors.
A lot.
So when you have errors, there's something you can always do is to restart runtime right here. Just run all, and that might fix your error because maybe sometimes you forgot to run a block of code previously, so the next cell will not run. Okay. So now we have the next thing we will do is to get our data for the model. So we will import the datasets, which is already built into the PyTorch, and we have already defined our transform here. So we will first transform data to the tensors, which is what we'll be using to train, and we normalize that. So we will be writing the dataset here. So first we define the training set. We will just say train set, and it will be equal to datasets dot mnist. And the parameters, the first parameter is root. So we want to go to a root directory. So root dot slash data, and since it's a training data set, we will set train to be true. For consistency, okay. So train to be true, and we do want to download the data set to our computer. So we will do download equals true. And lastly, we will apply our transform. So which is already defined from up there. So that's basically we have loaded this MNIST dataset into our notebook. So we copy the whole line and we paste it here, and we change that to validation. So valid. And the only difference is the train should be false now because we are using the validation dataset.
Hey guys, if you're having trouble following along, in a few minutes, I'm also just gonna put like the completed code also in that folder. So if you want to just follow along and then run the steps as we're doing them, feel free to go do that as well, since it might be hard if you're having trouble like typing everything out as fast as you are.
Okay, so don't forget to run the cell. Okay, we have problem. Transform is not defined.
Yep.
It's you put transform.
Okay. Thank you. Okay. So now all the data sets have been downloaded into a notebook, and we will move on to the next section. Okay, so since MNIST is a very big data set, we might not have time to train the whole data set. So we will use this block code to just use a small portion of the data set for training purpose. So we will take the first 3,000 of the training data set and the first 500 of the validation data set just to save time. So run this block of code, and you can see those two numbers being printed, which means we is rising. So now we have the data, but the data are just images. We have to find a way to organize data before we load them into a network. So we will be using the thing called data loader to achieve mini batch from the whole data set. So first we define the batch size, which is how many images you want to train in each iteration. So the number really depends on the computational power of your GPU. So if you have a very powerful GPU, you can change that number to a very big number, like 500 something. But it will save time, but it will also put a lot of pressure on your GPU. So it all depends on your GPU. So for our training purpose, we'll say it to be 32. And now we define the data loader we'll be using. So we do data loader, which is equal to bracket. So first we need a training data set, training data loader. So we do train, and it will be data, which is already defined by PyTorch. And the first parameter is the train set, and the batch size will be the batch size we define up there. And finally, don't forget to shuffle the data set just to ensure randomness. And we will copy the whole thing. And don't forget to add a comma here. Paste it here and change it to valid. And also here. So yeah. Everyone got that? Okay, so make sure you have train here and here and valid here and here. And we run the cell. Okay. Data loaders. Okay, sorry, forget S here. So it's data loaders. Okay, successful. Okay, now that we have our data loaders, we want to see how the image looks like. So we first define the classes, which is 0 to 9, and I have defined an image function called ImShow, which will show an image. And we have to get some random training image. So we will do images and labels equals. So we defined the train iter previously. So okay, train iter. We do train iter next. That will give us the next batch of images with these labels. And after we have that, we hit run. And you can see the whole batch of images, 32 images are being printed here. And the labels for the first row are also being printed. We can see they correspond to each other. So 4 with a 4 label, 7 with a 7 label. So make sure that's what you are seeing. Might not be the same image, but make sure the numbers and labels can match each other. Okay, so next, we are almost there. We have to define the loss function and the optimizer tool we will be using for our training. So first, we define loss function. We do criterion equals we're using the cross entropy loss, which is a very common loss function for deep learning, cross entropy loss. And for the optimizer, we'll be using optim.sgd, which is also a very common optimizer in deep learning. So its parameter, we have to pass in the model's parameter as its first parameter. So it knows which model are we doing the differentiation on. And also we have to specify the learning rate. We will start from a small number, say 0.001. And the momentum will be, let's say 0.9. So make sure you have that. And okay. And you hit run. Okay, so now we finally come to the step when we will be defining the train function. So if you look at the cell, is huge, I know, but there's not much you have to write. So first we will just do some variable definition, which is how many epochs we will stop, and the history, and the number of current epochs, and we set the timer. And now we come to the main loop. So the number of epochs is almost like how many iterations will be training the whole training and validation data set. So we will do a for loop, so for epoch in range number epochs, and we will initialize the train loss and the validation loss and the accuracy. We will set the model to be train mode and start the timer. And now here comes the training loop. So we will take a data loader, get some batches for each iteration, and with the data and target. We will turn on the model to be using the GPU, and we will do clear gradients on the optimizer. And here comes the actual forward path. So it might look very complicated in the slides, but here it's just one line of code. It will be output equals model data. Super simple, just one line of code. That's why we are using libraries like PyTorch to help us to write the code, because it simplifies all the steps and it's doing the work on the back end. And now we have our output. We will do the loss function. So we will do loss equals criterion. And the first parameter will be the predicted output, and the second parameter will be the actual labels. Okay. And now that we have our loss, we have to go backwards, which is do the differentiation of these. So we will do first loss dot backwards. So that function is basically calculating the gradient of each weight. And the next we will do we will do optimizer dot step, which is actually updating all the weights, and that completes one round of training. And after that, you are updating the loss and updating the accuracy. And after each training loop, we also have to do one round of validation to see is our model doing well, is there any overfitting issue. So we do the same thing, but here we are setting the model to be evaluation mode, and also we iterate with data loader, and we set the model to be using GPU. And here we are doing the same thing. We do output equals model data, and same thing for loss function. So loss equals criterion, and output as the first parameter, and the labels as the second parameter. But the difference here is that we will not be doing the back propagation, since we are only evaluating the loss. We are not actually updating the weights. Yes, it should be target. So target. So make sure it's target and not labels, because it's different here. Okay, so make sure you have that. And everything here down below is just doing some calculation of loss and accuracy. and printing out some stats. So yeah, you are basically done with the model train function, and make sure you don't forget to run the cell. And we have finally come to the final step, which is actually doing the training. So you hit the run. So, okay, print so that happened because some of the tensors has been set to be used in the GPU. Okay, let me go back and rerun that. That's weird.
So if you got behind a little bit, you can go and access that. All the code is there. You can go through the steps and run it in order to train your image classifier. And then for the last step after this, we're going to be like creating our own test data set, which should be pretty fun.
No.
Supervised and unsupervised.
So one thing you can also do is to restart runtime, which is just reset everything if you are encountering problem about GPU and CPU, which happens a lot, to be honest. And we just rerun the code. Yeah, sorry, my computer is acting weird. Okay, still has error. Okay, so if your code is also having that error, I would suggest you to just use the updated version. So here's the completed version, because that one should have no error. So it has all the code we have. So we do the same thing, we copy to the drive. We connect to runtime. Okay, 2 minute sessions. Yeah, you don't want 2 minute sessions in the runtime. So you might as well terminate all your nodes before you connect to the runtime. And make sure you have turn on GPU. And we do the same thing again, just run all the blocks of code. And everything has been written already for you. So just do that. Okay, now it's working finally. As you can see, as you start the training, so for every epoch, there will be a training loss and the validation loss. And you can see the training loss and the training accuracy and validation accuracy is increasing as we proceed to more epochs. And finally, it will stop at almost 90%. So both training and the validation accuracy will pass 90%, which is very good. And next, we will run the some visualization to see more clearly. So you can see the loss are decreasing very rapidly, and also the accuracy is also increasing very rapidly. So here we have completed the training and validation steps. Now Terry will just introduce you to how to do the testing process.
Okay, yeah. So on top of this code, basically we wrote an additional part that allows you to do kind of like custom testing. So anytime you're using you know, like Google Colab as some kind of like online Jupyter notebook editor, a really like important thing that you could possibly do is probably mounting onto your drive. And what that means is you can store all of your like, you know, data sets and images on your own Google Drive and then access them from Google Colab. And so that's what this block is going to do below. When you run this, it's going to basically ask you to sign into your drive. And so I'm just going to sign into Charlie's drive by clicking on this link. Sign in. And you'll get an authorization code. And so all you have to do is copy that and then paste it back and press enter. After a few seconds, okay, yeah. So we got that success message that says mounted at /content/G drive. And so that basically means that we're connected to our Google Drive. And at this point, you can also run commands like you would in a terminal, except in your Google Drive. So for all I have to do is like prepend that with an exclamation mark. So if I click exclamation PWD normally gives me in my terminal the current directory that I'm in. So if you try that, it'll say /content. And so what you can do here is I have some commented outlines that basically make a folder called digits, and we're going to use this digits folder to create some custom tests. The right command here is make dir, which just means make directory. And then inside the digits folder, we're also going to create 10 subfolders labeled 0 through 9. And the reason for that is in the code that we're using later, we basically want a folder for each class of our data, and the folder name should be the class name. And so here I'm actually going to go through and like delete all of this like Bambi hack stuff, since that was just for me and Charlie. But actually, like you can do that, but we actually already have this. We already have this digits folder made, so we're just going to skip this step. But basically, if you don't want to go through the process of creating your own custom digits, I actually did that for you. So if you go into the shared folder, you can access this digits folder, and these are images of numbers that I created. So one option is, you can go through and make that directory and then create all of those digits yourself, which I'm about to show you how to do. Or you can just use the one that I created basically by downloading this folder and then re-uploading it.
So yeah, make sure you download the digits folder, and it might be in zip file. You have to unzip it, and you just upload to your My Drive.
Yep.
Yeah, by using the option like upload folder. If you go to your My Drive here, you can upload the whole folder.
So while I let you do that, I'm also going to show you how to create your own images. So we're going to put these images into the folders that we just created, and then we're going to apply some transforms to them. And so in order to create your own image,
yeah, don't forget to delete the Bambi hacks in the test folder.
I'm just going to demo it with the images that we have right now. But basically, you can see that the code will pull the images in from your custom test folder and then try to predict what they are. And so you can see that like actually the predictions are not all completely correct. So we can also see if we can try to make some better images. So if you're on Windows, you can just use something like Paint. But if you're on Mac, you can follow use an online tool like this called jspaint.app. And so I'm actually just gonna go here. Here's this one. Okay, so overall, it doesn't really matter exactly what size you make your images, since one of the transforms that we apply is resize. So each image will be resized to an image that's 28 pixels wide by 28 pixels long. However, you don't want to use an image that's much too big, since what's going to happen is when you resize, the resolution of that image is going to go down significantly. So it's possible that if you start off with a really big image, it might not even be able to detect the digit in the end. And so what you can do in this tool is if you go to image and then attributes, something like this will pop up. Why is it so zoomed in? Just refresh, I guess. Yeah, so something like that will pop up, and you can set the exact size to be 28 by 28. If you're on MS Paint, you can also basically like drag your like white box in order to be that size, and you can check the size at the bottom. And then with this tool, you can basically like create whatever you want. So what we know is that we want to have a black background, and then we want to color this white. So our zoom is not really working. Okay, thank you. But yeah, if I, for example, if I wanted to like draw a 7 here, kind of hard with track time. I can draw a 7, save that image, and then put it back into my custom test folder in order to see if the model that we just trained can see if that's a 7 or not. Whoa.
And also one thing you have to remember is that the size here is a total number of images you put into your digits. So 1, 0 to 9, all the number of images. So if you are adding additional images, make sure you also monitor the size.
Okay, yeah, so with that, like our demo is pretty much over. What we did was basically train this model to be able to identify images, and then we showed that, you know, it kind of works. We put in some custom images that I made, and you can also put in your own custom images and see if the model can identify those digits. Yeah, that's the end of our presentation. So I know we skipped over glossed over a lot of stuff. So if you have any questions about like the details, feel free to come up and ask us after it's over. Yeah, thank you.
Thank you.